So this is me. So I'm talking on the TS50729, which is the interface standard towards battery trains. So why do we make a standard on it? To support, of course, a phase out of diesel traction and to have less CO2 emissions in the rail sector. So you can see we are part of the 9XC. It has been decided in December 21 to start a working group. We are 25 members of 8 countries. A very long title, so it's everything on the interface between the battery train and ground. The draft is available, published in September, and a 4-month inquiry is ongoing. So please read the document and provide comments, let's say by the end of the year. Official end is somewhere middle of January, but it's quickly middle of January after the end of the year, so do it this year. So these are all the interfaces. The first part of the presentation is on the interface between the battery train and the charging infrastructure. So we see a mechanical, an electrical, and an operational interface. The other interfaces will be on the end of the presentation. So first, in any case, you will need a system design and dimensioning study. Why? Because if it's not a full electrification, it's likely because it's too costly to do the full electrification, so meaning you have constraints. So you need a coordination between the railway undertakings that are going to operate trains on the line. This can be freight and passengers, so everyone has to be checked. The train builders, so what battery will be on board, what are the capabilities of the rolling stock, and infrastructure manager. So it is on the expected train offer capabilities and dimensioning, what I already said. Crucial in this case is, for instance, are there parts on single track? Because that has a constraint on the timetable. What's the available storage capacity on board? If that's limited, this also has a huge impact on the dimensioning. And are there limits on the performance of the infrastructure itself, on the charging infrastructure? So for instance, you can take a limited connection to the power grid, but then of course you can't have a full charge when requested. The picture you see a very small charging of just a few meters over at contact line, which is one of the possibilities. And also you can see it's a 15 kV, in this case 50 Hertz, so it's not a standard system, but we will add it as extra system. We identified 4 types of charging infrastructure. The first one is typical on DC networks. The problem there is that you want to be able to charge on a higher current at standstill than standard permitted. So it's typically then in a standard TSI compliant electrification system, but in the station itself it's possible to charge on a higher current. The second type is the case in Norway, where they want to electrify a 700-kilometer line with just 5 substations, and each time electrifying some electrification islands. But you see around that hill that there are multiple electrification parts, likely because there are, for instance, tunnels or places where you can't put the overhead contact line. So one substation can feed even multiple electrification parts. The third and the fourth are not TSI compliant. So the first 2 were TSI compliant electrification systems. The third one is a non-TSI compliant, typical because it's a 15 kV, 50 Hertz. It's a request from Germany for having cheaper converters for the connection to the public grid. And it seemed for modern rolling stock it was just changing the software to permit to have also a 15 kV, 50 Hertz. There was nothing more else to do to adapt the trains. In the case of the Type 3, it's an electrification of a full station or a part of a station, so more than the Part 4 or the Type 4, which is just a part of the overhead contact, no, a part of the platform having a dedicated overhead contact line. All the rest is non-electrified, so only at standstill charging is possible in this case. Important is the transition from and to non-electrified lines. Why? Because such a train can create an arc when leaving an electrified part with still the pantograph up and still trying to get current from the overhead contact line. Also mechanically, there could be problems first on when the overhead contact line is going up, and certainly when it's going down again. If your pantograph is up, you will likely damage pantograph and or overhead contact line. But also in between, you might have bridges or tunnels that are too low, and your pantograph will just smash to the bridge and be on the ground. And of course, if you're another risk, it's maybe not a huge risk you might consider, but if you're raising too late your pantograph, you were not charging sufficient in your electrification island, and you might need a stop to charge if you're permitted to charge sufficiently at standstill. Otherwise, run a little bit slower, then you're longer in the electrification island, and you might be able to have a bit more current charged in the battery. And if you're putting up your pantograph too late, it might be on a place where you have more limits on the charging possible from your overhead contact line, or there's maybe already a second train on the same line, and you may not charge both on maximum current, so you might damage and overheat the contact line. How can you protect signaling? ETCS has possibilities, but of course ETCS has to be there. The signal, the packet has to be part of the ETCS, and Bart has to be able to cope with it. You can have a neutral section with the intermediate part connected to the ground, to the return circuit. Then of course you will have a short circuit, and it will be detected that you have to lower your pantograph. Or you can have a vertical fading of your overhead contact line, and then a device checking that the pantograph reaches a certain level and then drops the pantograph. But typically there is no automatic recovery when this automatic dropping device has been activated. So it's not the best way. It's a last resort to avoid damage, but you will have a problem to lift up again your pantograph on the next section. Current at standstill, which is a typical problem on DC networks. On AC, it's typically you can charge sufficiently at standstill, but on DC, you can see the table below. On 1.5 kV, it's 300 amps. On 3 kV, it's 200 amps. It's not sufficient to charge a train. We want to have 800 amps possible, and you will see on the next slide some possibilities on how to do this. A first, which is sufficient for AC, is just double the contact strip. You can use 2 fixed contact bars, and if the distance is sufficient between the bars, then you can increase the current taken at standstill. Also, if you have a higher contact force, you can also have higher currents. For DC, we are looking on having 2 contact bars, but making contact with the metal part of the pantograph. So not a carbon strip, but left and right of the carbon strip is copper or aluminium of the pantograph. On that place, it will be possible to have higher current taken from the overhead contact line. Why don't we do it then always that way, or why don't we use always a metal pantograph? Of course, because that would damage too much the pantograph. But here it's intended for very low speed and standstill. In that case, it's less critical. An operational interface is needed to send information on the limit of charging current, the limit on the maximum current at standstill, and the maximum feedback current. It might be for some maintenance purpose that you want to discharge your battery. In that case, you need to know how much can I discharge via the charging infrastructure. How? It's very open in the technical specification. It can be manual, automatic, via the voltage or frequency modulation, or a communication protocol, or by any other means. Some of the means are you can use maybe a direct communication to the TCMS. A request is sent to ERGU of Europe's Rail to check in the system pillar if there are possibilities on having such a direct link with the TCMS. And it is already included in the communication from traffic management to automatic train operation and to driving advisory systems. But if you send it to a driving advisory system, of course you still need the interface to the board. It can be the driver, but then there should be sufficient checks that the driver has done it. Otherwise there is a risk of what I've shown on a few slides before. So now all the other interfaces. I will go very quickly through the other interfaces. You can read the TS in the next month and provide your comments. So the distribution grid might have limits because you just have a medium voltage connection with limitations. Limited power, limited short circuit power, permitted harmonics might be limited, the unbalanced current limits and reactive power requirements. All these can give constraints on the charging of the train. Be careful also with the train detection system and the signaling. Where will you put such partial electrification or such a charging station? It's typically on a place where there was no electrification. So it is new. You want to do it low budget, but you have to be careful that you don't harm existing systems of the train. The railway infrastructure, of course, if you're electrifying, you have to check also the clearance distances, for instance, to a roof equipment of a platform or of tunnels, of bridges, because it was before a non-electrified railway infrastructure. Traffic management, optimize the charging process, might be needed and might have impact on the timetable. So if you're arriving late, you might need a certain time in a station before you can return. Traffic management shall be informed also on the earliest departure time, because then it knows what will be the conflicts in the rest of the journey. And extra information can be exchanged to optimize the using of the charging infrastructure. If you have reserve, then you can optimize, but that's the latest part. Signaling of the transition from and to electrified section. So rising and lowering of the current collectors and switching on and off of the circuit breakers. It has to be put sufficiently before you have to do it. There are different possibilities that can be a result of the risk analysis. It can be fully automated. It can be automated up to the display of the driver, but the driver then acts. It can be the lateral signaling, as you see the boards on the right side. And it can be just a written or a vocal information and the driver has to execute it. Of course, the lowest has the lowest safety level. The last part is easy. On onboard energy measurements and on energy settlement, just use the existing standard, the EN 5463, and all energy taken from and returned shall be measured. It's also TSI lock and pass requirement. All data shall be transferred to a data collecting system on ground, that's the energy TSI, and the handling on ground is done by the IRS 9930, and you will have a presentation on it tomorrow. And the settlement shall consider that there are higher consumptions during the charging and that you might have, or you will have, trains running without consumption, which is maybe not foreseen in your settlement system at the moment. And that's then the last slide with the outlook. So as said, it is published in September the 19th. You have 4 months inquiry now. It is published on the 9XC fixed installations and in parallel on 9XB because it's also dealing with rolling stock. We want to have FPR by June 24 and a TS by end 24. But after that we will have some experience and then likely go in again a maintenance phase and maybe make an EN of it. But please read now the PRTS and provide your comments. Thank you.